Okay, so let's analyze the next fit algorithm first. So analysis of next fit. So we are at beam packing again. So first, remember that we are trying to prove bounds for the asymptotic competitive ratio. So for a bad input, we first have to fix n and give a bad enough input sigma width. We have to ensure that the optimum value for this input sequence is at least n. Now, if you remember the bad input for next fit, it was 0.9, 0.2, 0.9, 0.2 and so on, and that's almost good, but if you have many 0.2s, then they won't fit into one single bin. So just let us consider, let sigma be the following input. So it's, say, 1 over n, and then I'm having 1 minus 1 over 2n. So two of these objects won't fit into a single bin, because 1 over, say, if n is 20, or let it be 5, then the first one is 1 over 5, which is 0.2, and the next one is 1 minus 1 divided by 2 times 5, which is 0.9. So that's exactly our previous previous bad input example for the case when n equals 5. So these two guys won't fit together, but the small guys would fit together if there is only n of them. So that's our input. Actually, so in total there are n objects of size 1 over n, and also we have n objects of size 1 minus 1 over 2n. Now clearly the next fit algorithm, similarly as before, will pack these into separate bins, because 1 over n, so next fit will just behave as 1 over n being placed into one single bin, and then since the second guy doesn't fit, it will be closed, and it's just 1 minus 1 over 2n, but the next won't fit, and the next won't fit, so the next fit's cost is 2n. Okay. Now, the optimal solution, however, is to put all the small objects into one single bin, and then we just put all the large objects, which almost fill their bins anyways, times n. So the optimum is, in this case, n plus 1. Now this means that if you recall, so for each n I can give a bad input on which the cost is 2n and the optimum is n plus 1. It's almost twice as large, not exactly, but almost twice as large. So if you just recall the limits, it was the formula of the for computing the asymptotic competitive ratio. So it was okay. So it was next fit in this case for sigma divided by the optimum value for sigma, but only for those sigmas for which the optimal value is at least n. Now, for any n, this sigma is a part of this set, is a member of this set. So the supremum is at least. So the supremum is at least 2n divided by n plus 1. It might happen that there is an even worse input for these n's, but it doesn't really matter, because it means that the limit of a sequence in which each element is at least 2n divided by n plus 1, this is just, of course, it's just at least as large as the limit. Oops. At least as large as the limit with n tending towards infinite of 2n divided by n plus 1, which is actually 2, right? So you just divide by n, so it's just 2 divided by 1 plus 1 over n, which is just 2. So this means that the competitive ratio of next fit is at least 2, right? The asymptotic competitive ratio. So that's for a lower bound, and for an upper bound, we just consider some input sigma, and backing computed by next fit. So you have a bin, you have some objects, so the total size used in the first bin, let it be x1, and the next bin is filled up to x2, and the next bin is filled to x3, and so on. So there are at least one, but possibly more objects in each bin, and of course we used the last one, so it's x, say t. Okay. Now, an important thing to realize is that the sum of these two bins sizes, x1 plus x2, is, well, it's more than 1. Why? Because we opened a new bin. We opened the second bin because an object arrived which did not fit into the first bin. Did not fit means that the total content of the first bin plus the size of the first object in the second bin is already larger than 1, which means that the total content of the first plus the total content of the second bin is more than 1. And of course the same thing happens with these two bins, so x3 plus x4 is at least 1, and so on. Now it might happen that t is odd, it might happen that t is even, but nevertheless it's true that if it's even, then the whole sequence, so it's t minus 2, it's xt minus 1, say, and it's xt, why not? So the sum of these two guys, xt minus 2 plus xt minus 1, is again at least 1, and there is one missing element. Or it's even, in which case I can just sum the whole sequence, and it will be larger than t divided by 2. So if t is even, then I get that the total sum of these sizes, which is actually the total sum of all the objects, because we packed all the objects. Now this will be at least t half, and for the case of t being odd, we just know that the sum of the, well, t minus 1. Okay, so if odd, then it's left out, but if I just sum all the previous ones, then well, this is just smaller than or equal to the size of all the objects. But this thing is at least t minus 1 half. So, and of course I also know that this thing, the sum of the objects, this was the only bound, only lower bound for the optimum, so this is at most the optimal value. This is at most of sigma, and t is of course the next fit's output, because we are using two t boxes, so it's the next fit's cost divided by 2, and this is just the next fit's cost, well, minus 1 divided by 2. So either t is odd or t is even, we get that well, in both cases the next fit is smaller than the optimum, or the next fit minus 1 half is smaller than the optimum. So in all cases we get that the next fit minus 1 divided by 2 is at most at least, okay, it's just the optimum. So I can just divide by the optimum and multiply this by 2, and I get that the next fit minus 1 divided by the optimum is actually at most 2, and I can also add 1 over optimum, and I just get that the next fit's output, divided by the optimum is at most 2, well, plus 1 over the optimum value. Now again, if I'm just substituting these things back to the formulae I had, so the limit superior of well, so if the optimum's cost goes to infinite, okay, and then I'm just taking the supremum of the next fit divided by the optimum value. Okay, so it's just sigma, so oft sigma is at least, say, opt, okay. Then by this I get that the supremum is at most 2 plus 1 over opt, so this limit is just the limit of optimum tending towards infinite, 2 plus 1 over optimum. which is 2 again. So we had a lower bound of 2 for the next fit by a bad input family, and we also have an upper bound for this value, which works for any possible input. So this means that the competitive ratio, asymptotic competitive ratio of next fit is exactly 2. And that's the result about the next fit. Yeah, great. So in the next part I will try to analyze the other algorithm, which is called the harmonic algorithm, and which we call by a parameter k. Till then, bye bye.